Hello and welcome to video 5 of my ISM product series. If you haven't watched the previous videos, please go ahead and watch them. They provide some really helpful context. So an overview of this video is that we're going to explore simulations of steering galactic devices and spin. And to do these experiments, I'm going to use a simulation. It's on the web browser. So if you want to follow along or just like mess around with the website itself, you can go to it and put the link on the screen. So here is the simulation website. This white box contains the simulation itself, and within this white box, you can move around the respective elements. So you can delete individual elements by just dragging them out of the space, like this. And you can create new elements by taking the beam from the furnace and this dropping it onto a empty space, and then this um, menu will pop up, and then you can pick either an analyzer or counter. And then from each analyzer, you're going to see there's two arrows, up and down. These arrows correspond to spin. So spin up will be coming out of this node, and spin down will be coming out of this node. So if you click on the node, we can drag and drop a counter. And same for the spin down node. To see how many particles are spin up and spin down, we measure the particles in the x-axis. We can also change the axis of measurement from x to y or z. These analyzers are just basically stir and collect devices. So here is the first question. In the state that is in right now, is the spin measurement for a singular particle predictable? So the answer is no. You can't definitely tell if the particle will be spin up or spin down. You can only give approximations, and it'll be a 50% chance it'll be spin up and a 50% chance it'll be spin down. So to simulate that, we can just click 1 and see where it goes. Spin down. Before clicking that, we would have no idea if the particle will be spin up or spin down. So as we know that the probability of a spin up or spin down measurement will be 1/2, what can you tell about the results of the second analyzer given this setup? So by running the simulation, we can find that out. We see that in the second analyzer, we only get spin up particles. But why? So to understand why we only got spin up particles as the result for the second analyzer, let's take a look at probability one more time. In the previous videos, we had a different version of probability. We had maybe a plus or minus sign for the bra vector, or spin up, spin down, and psi as a ket vector. But in this situation, we have out as the bra vector and in as a ket vector. So what we were really doing in the previous videos was just a applied example of this format, where in is just the beam coming into the analyzer, and out is the spin up or spin down probability that we're trying to calculate. So in the previous videos, we had the plus sign, the spin up bra vector, and the psi as a ket vector, and the psi had a function attached to it, which we then converted to a matrix, and then we calculated the probability of finding the spin up or spin down for that particular function of psi. So if we can apply this format to the simulation, we can understand why we only got spin up as the result for the second analyzer. As we take another look at the setup itself, we see that the input for the second analyzer comes from spin up particles from the first analyzer. So the input for the second analyzer is the spin up particles from the first analyzer. So using this knowledge, we can go ahead and set up our probability equation to find out the probabilities of spin up and spin down for the second analyzer. As we've seen from the simulation, the particles coming into the second analyzer are just spin-up particles from the first analyzer. So the input is just the spin-up ket vector. And then the output that we're trying to find, let's say it's going to be spin down. So spin down for a vector is just 0, 1. And the spin up ket vector is just 1, 0. So by using this formula, let's calculate the probability. So the probability of finding spin down will be equal to the absolute value of the inner product squared. So replacing the notation with the matrix equivalents, we have 0, 1 times 1, 0. Continuing, using matrix multiplication, 0 multiplied with 1, leaving us with 0, plus 1 multiplied with 0, leaving us with 0 again. Adding the two quantities, we get 0 plus 0 equals 0. And as 0 squared is also 0, the probability of finding a particle spin down is 0. This correctly matches what we've seen in the simulation itself. We found 0 particles being detected as spin down in the second analyzer. Let's keep going. Instead, this time, we'll say the output, as a spin up raw vector. And the input stay the same. Setting up the equation, we get one zero times 1, 0. Performing the matrix multiplication, we have 1 times 1, which leaves us with 1 plus 0 times 0, which is 0. And 1 plus 0 equals 1. And then squaring that, we get 1. So the probability of finding a particle spin up in this particular situation is 1, which we see in the simulation itself. All the particles that came into the spin into the second analyzer, were all recorded as spin up. So now on to a similar example. So we have a similar setup, but instead of the second analyzer being oriented in the z direction, now it is oriented in the x direction. So what changes, if any, will be made in the results of the second analyzer? Let's see. We see that unlike the prior experiment, the second analyzer has both spin up and spin down quantities recorded. But why? So we see the results of this experiment are quite interesting. Even though that the input to the second analyzer were all spin up particles, we still find that there are spin up and spin down particles recorded as the outputs. We have spin up particles in the z direction that are as the input for an X analyzer, a analyzer which only measures in the X direction, the spin in the X direction. This experiment goes over the concept that even if a particle is known to be spin up in one direction, or if the spin is known in one axis, its spin in the other axis is indeterminate. And as we see in the experiment, there's basically a 50-50 split of spin up and spin down for a spin up particle in the z direction. So we can represent that as an equation. So spin up in the z direction can be rewritten as 1 over the square root of 2 spin up in the x direction plus 1 over the square root of 2 spin down in the x direction. So why these coefficients? Well, as I told you in the previous videos, the coefficients squared when added together must equal 1. So if you take the square of 1 squared 2, we get 1/2. And since they're the same, this value will be the same for both of them. And 1/2 plus 1/2 equals 1. So that condition is met. So since we now know how this particle can be rewritten in other directions, specifically the spin up beam in the z direction can be written as components in the x direction, we can write all other spin up or spin down components as their counterparts in the other directions. So for example, spin up in the x direction can also be rewritten as 1 over the square root of 2 spin up in the z direction. Remember, there's no subscript for the z direction, it's already assumed. Plus 1 over the square root of 2 spin down. Likewise, we can rewrite the spin down in the x direction as components in the z direction as 1 over square root of 2 spin up minus 1 over square root of 2 spin down. So for spin down ket vectors, instead of having the second half or the 1 over square root of 2 spin down as an addition, you have to use a subtraction. So to make math a bit easier, let's convert these ket vectors into their matrix forms. Like in the previous video, I expanded the equations and condensed them to a matrix form. I did the same with the spin up in the x direction and spin down in the x direction, and I converted them into the matrix form. That should be negative. My bad. So we can substitute them into the equation for the spin up in the z direction so that we can get the matrix for the spin up in the z direction. So continuing, we have spin up in the z direction as 1 over square root of 2 times spin up in the x direction, so 1 over square root of 2 over 1 over square root of 2 plus 1 over square root of 2 times spin down in the x direction. So 1 over square root of 2 times 1 over square root of 2 over negative 1 over square root of 2. So multiplying this out, we can get spin up in the z direction as 1/2, 1/2 plus 1/2, negative 1/2. So that gives us spin up in the z direction as, my bad, 1/2 plus 1/2 and 1/2 minus 1/2. And as you see, we get 1, 0. Just like how the original definition of spin up in the z direction was 1, 0. By breaking it down into its components, we still get the same answer. This just shows that all spin is just components of other axes of spin. We could do the same with using the components of y instead of using components of x for the spin up in the z direction, and we still get the same answer. So we have the input as spin up in the z direction as 1, 0. And the output, let's say we want to find spin up in the x direction, so this. And since we already know what the spin up in the x direction is in its vector in its matricy form, as 1 over square root 2, 1 over square root 2, we'll just use that. And so just converting this to its broad form, we just flip it on its side. So we get the x direction, as 1 over square root 2, 1 over square root 2. So now we'll go ahead and complete the probability. So continuing, we need to find the spin, the probability of finding spin up in the x direction with the input being spin up in the z direction. So we write the bracket vector, the bracket notation as spin up in the x direction times spin up in the z direction. So this is the probability. So as we know that the matrix for this is would be 1 over square root 2, 1 over square root 2, and the matrix of that spin up in the z direction is just 1, 0. Multiplying this, we would get 1 over square root 2 times 1, which would be 1 over square root 2, and then 1 over square root 2 times 0, which would be 0. So we get our answer as 1 over square root 2. That's just the inner product. So now we need to square that. Squaring that, we just get 1 over square root 2 times 1 over square root 2, which is 1/2. So this says that there's a 1/2 probability, a 1/2 chance that the spin will be spin up in the x direction given a beam of particles of spin up in the z direction, which we see in the experiment. And with that, that concludes our video. Thank you for watching, and please complete the Google form afterwards. Thank you again for participating in this project.